In this video, we're going to prove the Moore's theorem. Basically, it says that if you have cosine theta plus sine theta to an integer power, then you can basically just multiply the angles by that integer. Now, we'll do two proofs. One very quick proof, and the other proof which is pretty much the standard one, which is proof by induction. So how about we say proof 1. We know from Euler that e to the I x is equal to cosine x plus I times the sine of x. And this is our function. That is, whatever I plug in for x here, I have to plug in for x here. So let x equal nt. And we're going to evaluate this equation two different ways. E to the I times nt. Well, on one hand, that's cosine of nt plus I times the sine of nt. Okay, now we could compute that a second way. E to the I times nt. This is e to the it raised to the n. But this is only for n being an integer. Not going to get into y. So e to the int is equal to e to the it raised to the n. But what's in the bracket is cosine of t plus I times the sine of t raised to the nth power. So basically, I wrote this two different ways. I wrote it like this and I wrote it like that. So this and that should be equal. Therefore, cosine of t plus I times the sine of t raised to the nth power is equal to cosine of nt plus I times the sine of nt, and this is for all n in their integers. And the proof is done. Few lines. So let's do it also by induction. See if I can make this any bigger, any longer. Okay, so proof number 2 by induction. Now, when it comes to, say, integers or any real numbers, I like to think that there are three types of, in this case, integers. Positive integers, negative integers, and the number 0. Okay, assume n is positive. Okay, so if n equals 1, we want the cosine of x plus I times the sine of x raised to the first power to equal to cosine of 1 times x plus I times the sine of 1 times x. Well, The left side, anything to the first power, is just anything. And the right hand side, well, cosine of 1x is the cosine of x plus I times the sine of, well, 1x is x. So yes, it's true. Okay, so for n equals 1 is true. So now assume true for n equals k. That is, assume the following, that cosine of x plus I times the sine of x to the kth power is equal to cosine of k times x plus I times the sine of k times x. Okay, we assume that. Now, we must show for n equals k plus 1 the following. That the cosine of, yes, x plus I times the sine of x to the k plus first power, does it really equal to cosine of k plus 1x plus I times the sine of k plus 1x. Is that true? Well, let's get our hands dirty and find out. The cosine of x plus I times the sine of x to the k plus first power. Well, since we know how to handle when this is raised to the kth power, let's do that. That is, let us break off k of what I just wrote. There's k of them times the last one, the k plus first one. Now, the first factor, by assumption, this is cosine of kx plus I times the sine of kx. And all of this gets multiplied by cosine x plus I times sine x. Alright, now let's get the real parts. This times that, well, that's a real part. That's cosine of one angle times cosine of another angle minus, because when you multiply those two with positive I times the other positive I will give you negative 1, and we get the sine of one angle times the cosine times the sine of the other angle. Sorry. Put that in parentheses. Plus the imaginary part. Well, this times that will be imaginary. The cosine of kx times the sine of x. And then this times that will be imaginary. We factored out the I, so we get sine of kx times the cosine of x. Now, this here is the cosine of kx plus x plus I times that. Well, that's nothing more than the sine of kx plus x. Kx plus x. I didn't need those brackets. And this becomes, factoring out the x, becomes k plus 1 times x plus I times the sine of k plus 1x. That's exactly what we wanted to show. So for n equal positive, when this exponent when this exponent is positive, no matter what it is, positive integer, it really does distribute. Now, let us look at when n is equal to 0. So, is the cosine of x plus I times the sine of x to the 0 power, does it really equal to the cosine of 0 times x plus I times the sine of 0 times x? On the left-hand side, anything to the 0 power is 1. On the right side, 0 times x is 0, plus I times the sine of 0 times x is 0. Cosine of 0 is 1, plus I times the sine of 0 is 0, and I times 0 is 0. And yep, 1 plus 0 is 1. So it does work for n equal 0. So now we're going to go on to when n is negative. Note that the cosine of x plus I times the sine of x to the negative first power, well, this is equal to 1 over cosine x plus I times sine x times 1. I'm going to write the 1 as the complex conjugate of the denominator. Now, 1 times the numerator, hopefully that's pretty simple. And the bottom, you're going to get cosine x times cosine x, which is cosine squared x, and then minus I sine squared x, and then you're going to add that back. And then you're going to multiply this by that. Positive I times negative I is negative I squared, which is plus sine squared x. And that denominator is 1. And anything divided by 1 is the anything. So this is equal to that. So what I want to show is, so that basically, if you have cosine x plus I times sine of x to the negative case power, this is equal to cosine x plus I times sine x to the negative first power raised to the case power. But we know what's inside those brackets, the big ones. It's this. We just derived that. Minus I sine x to the case power. Now, remember, we want to say that I multiply the angle by k. Sorry, by negative k. This is, well, here. Now this is the one we want to prove. Can I distribute the k? Well, that would give us cosine of kx minus I times the sine of kx, and cosine of kx is cosine of negative kx, and if I put this negative inside, I get plus I times the sine of negative kx. So I want to show that this equals that. That being, just take the power and multiply it by the given angle, which was x. So the only place where we're not sure is if this equals that. Now note that somewhere I should have said that k is positive. Okay, k is positive in all cases. because we want the power to be negative. Well, if k is negative and you put a negative in front of it, it becomes positive. K has to be positive. We're assuming that k is positive. So like I said, we want to show that 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 this equal sign is valid. Because if we do show it, then we're okay. Show that the cosine of x minus I times the sine of x to the kth power is equal to cosine of kx minus I times the sine of kx, for k in the positive integers. Okay. So if n is equal to 1, you have the cosine of x plus I times the sine of x to the first power. Does it equal to cosine of 1 times x minus I times the sine of 1 times x? Answer is yes. Anything to the first power is itself, and 1 times x is just x. So yes, we did get what we want. We got this was supposed to be minus. I apologize. So it's true for n equal 1. So now we assume that it's true for n equals k. That is, the cosine x minus I times sine x to the kth power is equal to cosine of kx minus I times the sine of kx. We assume that. Now, we must show for n equals to k plus 1 that the cosine of x minus I times the sine of x to the k plus first power, that this is equal to the cosine of k plus 1x plus I times the sine of k plus 1x. That's what we have to prove. So here's the proof. Cosine of x minus I times sine of x to the k plus first power. Well, I'm going to factor out or break off k of those bases, that being the base. Factored off k of it times the extra one. Now, the first factor to the kth power, we know, or we're assuming, that it is this. Times the second factor. And like the other half of the proof, let's get the real part first and then the imaginary part. This times this, which is cosine kx times cosine x, going to be minus, because this times this, well, a positive I times a negative I is negative I squared, which is plus I. This is supposed to be negative. It was negative. Okay, so negative I times negative I is going to be positive, and you're going to get sine of kx times sine of x plus I times. You multiply this by that, even factor out the minus sign. Excuse me, you factored out the minus I, so you're going to get cosine of kx times sine of x. And now you multiply this by that. You already factored out the minus I, so it'll become plus, and that's going to be the sine of kx times the cosine of x. And you put brackets around this. Now the real part, that's the cosine of kx plus x minus I times, this is going to be the sine of kx plus x. So we end up with the cosine of k plus 1x minus I times the sine of k plus 1 times x. And that's what we wanted to show. It's true for positive integers, the Moivre rule. It's true for n equals 0, and it's true for negative integers. Leave a comment about this one. Let me know if you think I could have done it any shorter in the induction method. Let me know how you like the first proof, which was just a few lines, whereas this proof was 2 pages long. The other one was, well, 3 pages long, and the other one was just a few lines. Oh, 4 pages long, and the other one was just a half a page, and I wrote big. Most of all, watch and learn.